Hi, this is Miss Litton, and this is my wonderful, this is lunch. Say hi. Say hi. Hi, okay, we're eating. And this is Honors Biology, and we are reviewing chapter 24. So 24 is basically central dogma, right? So if you want, in a nutshell, I have it at the very end. I think, maybe I don't. Darn it, it's in that other one. Okay, never mind. Okay, so in a nutshell, we want to talk about how DNA, central dogma, goes to what? RNA to what? Protein. Good. Okay, so that's in essence what this whole chapter is about. So for DNA, when DNA makes more DNA, what is that called? Replication. And you would want to know the steps in doing that. When DNA goes to RNA, what is that called? Transcription. And you would want to know the steps in that. And when you use RNA to build a protein, what's that called? Translations. And you would want to know the steps in that. Okay? Now, let's start with a couple of things. On DNA, let's talk about what we learned. In DNA, we learned about the structure. What is the structure of DNA? Double helix. Okay. Who came up with that structure? What were some of the scientists, the key scientists? Yes.
Crystallized diamonds, something with the
okay. Wilkins, right? And Rosalind Franklin. Okay, but before that, who was the first one we talked about? I would always chase down a Hershey and Chase. Okay, do you remember what Hershey and Chase worked with?
Bacteriophage.
Yeah, they worked with that bacteriophage. Do you remember that?
They labeled it with like the label.
Yes, they P32. Oh, sorry, P32, and what was the other one? S35. Okay, so we had phosphorus and sulfur, and the P32 labeled the DNA inside, and the sulfur labeled the protein coat. And they were wondering, what is it that gets passed on? And what they found out is the radioactive phosphorus is what gets passed on. So that had labeled the phosphates in the nucleotides of DNA. So they were able to say that was the transforming agent in the bacteria. And yes, they did work with a blender, right? So that was one of our earlier experiments, and that's what you saw here, right? And they did not actually know the structure of a bacteriophage because they didn't have the microscopy to see that. Okay, so P32 labeled the DNA and it went inside, and then they separated it, and they used a centrifuge to spin it down, and the phosphorus was in the bottom. All right, next, who was another scientist you said? Will, remember? Franklin and Wilkins, okay? And what did they do? What did they contribute? You said it, the what? X-rays, right? And they found out that the DNA had repeating units in it. What else did they find out? It was helical and of constant diameter. Okay? What was another scientist? Remember I showed you in his younger self? Chargaff. And Chargaff said that Rosalind Franklin and Maurice Wilkins on this one. Okay? And what did Chargaff say? That the number of A's equaled what? Number of T's, and the number of G's equaled what? Number of C's. Okay, then who put all of that together for the structure of DNA? Watson and who?
Crick.
Watson and Crick. Good job. And when we study that, if we take that double helix and we iron it out flat, okay, we would see that adenines always bind with a what? Thymine, and how many hydrogen bonds between them? Two. And we would know that guanines always bind with who? Cytosines, and how many hydrogen bonds? Three. And then we know that those nitrogenous bases are attached to what? sugars, and then those sugars are attached to phosphates. Okay, and we know about 3', 5', right? Leading, lagging when we talked about DNA replication. Okay, and so I'll go over that structure with you too, so you have it. All right. Moving. Let's look right here. Or here. Okay, so we know that this right here would represent a what? What did I just circle?
Nucleotide.
That's a nucleotide, good. Okay, what's the name of this right here? What is that? Sugar, and what's the name of it? Deoxyribose. Okay, and what do you call these bases right here with 2 rings in them? Those are purines. And the single ringed ones are called what? Pyrimidines. And you always have a purine attached to a pyrimidine. That keeps the diameter constant. You always have a 2 ringed with a single ring. Okay, then when we look at something like these, when I look at this sugar right here, I know that carbon number 1 is the one that's connected to the nitrogenous base, right? And I don't go on the roof because on the roof you have what? Oxygen. I come down and around, that's 3, up 4, chimney makes 5. Even if my house is upside down, I can still number it in the same way. And that's how I could tell leading and lagging strands. Jump to here, and you can, okay, I want a question. Where are you? There we go. Oh, okay. Did somebody who made that list? I didn't start one yet. Is that one that's complete? Here, we'll find one. Let's do Finding Nemo.
What's the number?
Did it start yet? 21 number. Okay. There's more than 9 of you. You should be testing yourselves. Okay, good job. He touched the butt. So they did find the phosphorus inside, and you're going to remember that because base, sugar, what? Base, sugar, phosphate in a nucleotide. So you're going to remember phosphorus is inside. Base, sugar, phosphate. Phosphorus was found inside because it labeled the nucleotide. Yay! 1. Here, let's go in. Let's do one that's not as obvious. Okay, how do we do? What did somebody put? Okay. All right, so 15% of the bases were cytosine, was 15%. Who does cytosine always bind with? Guanine. So 15% would also be guanine. What's 15 plus 15?
30.
30. What's left? 70. So we have to divide that amongst the other two. Questions? I'm assuming it was a silly math mistake. Alrighty then. But don't make that on the quiz. Alright, then we talked about DNA replication. You want to remember the key word in DNA replication is that it is what? Semi-conservative. Excellent. Okay, and that each original strand serves as a template for a new strand. So you have an old and you have a new. And if I told you the sequence of bases, you could pick the right answer, right? And tell me, for instance here, you would tell me what's the sequence of bases that would be complementary here?
A, T, G, C.
And our song that we learned, Zero Period came up with the idea of recording it. So this whole thing, Boom Boom, Twist Up, Sister Chromatids, Put Away, Cap Tail, all of that is on YouTube right now if you need if you want that. Okay, and let's go over the enzymes. What does helicase do? Unwinds and unzips. Good. What does DNA polymerase do? It does the boom boom. What does that mean to boom boom? Look, you guys still know the song. They're all back there going. It brings in the free nucleotides. Good. Exactly. All right. And what does ligase do? Seals the phosphate sugar backbones. Good job. All righty. Here you go. Remember, you're not going to use words like change into or becomes, right? One strand always serves as a template to make another strand. It's not changing into another strand. It's serving as a template. Yay! Good job. Just tell me the answer to this one because I want to go quick on this one.
B.
What's the answer?
B. B.
Yeah, I agree, B. What's the answer to this one?
C.
C, ligase. Good. What's the answer? Oh, okay. Could you do this? No problem. Okay, I'm going to point to something. You tell me what it is. I'm pointing here. What is this? My gosh, be a pin. It's what? Guanine. How did you decide that this was guanine? 3 hydrogen bonds, so you know it has to either be C or G. And then you knew what? Purine is the bigger one. Pyrimidines, remember 4 primitive pyrimidines, they only have 1 ring. Right? And if I pointed to this one, you know it has to be a combo of a adenine and a thymine. And you know that it's the sugar that's connected to the nitrogenous base. Phosphates are only connected to other what? Sugars. Right? A phosphate, if this is a phosphate, the only thing he's connected to is sugars. Whereas sugars are connected to what? 2 phosphates and a base. And nitrogenous bases have a hydrogen bond between themselves and another base and a sugar. Yes?
Can you clarify which one's the lagging strand and the leading strand?
Yes, I can. It depends on where you're looking from. If my eyes are up here and I am looking from here, and this is where the enzyme is starting, up here at the top, okay, then let's go right here. This right here, where the nitrogenous base comes in, this is going to be carbon number what? 1. I can't go on the roof, okay? So I'm going to come up here. This is carbon 2. This is carbon number what? 3. So this is the 3' end. The 3' end is always the leading strand because it's DNA polymerase 3. This one over here would be the lagging strand. This is carbon 1, can't go on the roof. This is carbon 2, this is 3, this is 4, chimney makes 5. That would be the lagging strand. So the DNA polymerase would have to go, oh, and turn around and approach it from a 3' end and work its way backwards to copy it. Yes?
So the sugars that are like facing up as a house are always the 5?
Don't think of it like that. You want to see. Okay? Yes.
But how do you know to stop at 3 for the other one? Like, and not continue like 4 and then 1? Because you stopped at 3, but why can't you go?
Oh, because I'm looking at the outermost edge here. The top outermost edge. At the top, yeah. Yes?
How do you know where to start? Which one's 1?
Oh, there's 5 carbons in this sugar, right? 1 is always the one that's connected to the nitrogenous base. That's always carbon number 1, no matter what. Okay. All right. Next. We talked about RNA. RNA is different from DNA in 3 ways. What 3 ways? Sugar. The sugar is different. What's the name of this sugar? Ribose. What else? Oh my gosh, it's already labeled. And what else? Single strand. And you have uracil. Good. And when we look at this, okay, this should be a review diagram for us, right? So you're using the DNA to make what? mRNA. Now you've got to process that mRNA after you make it. You've got to put on a cap and a tail and cut out the introns before you leave the nucleus. So now that's why they call this mature RNA, because it's been processed. Once it goes out, it's going to have to hook up with small and then large what? Ribosomal subunit. Every 3 bases on the mRNA is called a codon, and that's complementary to an anticodon that's located on the tRNA. T stands for transfer. What is it transferring?
Amino acids.
Amino acids. When you hook amino acids together, you have a protein. When you use DNA to form RNA, both DNA and RNA are nucleic acids. Yes? So I am speaking the same language. I'm speaking nucleic acid language. It's like I'm saying the word hello and I'm writing down the word hello. It is still English, right? But in translation, I'm changing it to a new language, hola. I'm changing it from nucleic acid language to protein language. Yes?
Yes.
Okay. All right, now, so when we do DNA replication, we're copying the whole thing. But when we do transcription, we just need information in here about one gene. So we have to know where to start. Where are we going to start? RNA polymerase binds to the promoter. And that's where transcription will start, is on the promoter. And what we're going to learn in the next chapter is controlling the promoter controls a lot, whether or not RNA polymerase can bind on there. Okay, and then this brings us back to our central dogma again. So you should know now how to make RNA from DNA. Then we use that RNA to make a protein. Now you're using, who's the message? mRNA. That's the one we always look up on the codon chart. So if I tell you here, okay, if I say this is the DNA, you could tell me what the complementary, if I was doing replication, you could tell me what the letters are, right? And then you could tell me what the mRNA is going to be, right? Because it would be complementary. So what would it be right here? G. A. Good. Okay. Now, if I gave you the DNA and I said, tell me, please, the tRNA, could you do that?
Yeah.
What's the tRNA going to be right here?
C. A. U.
U. Good. Okay. And that tRNA is going to transfer an amino acid. Could you tell me the name of that amino acid? What would you have? You'd have to use the chart. And what am I going to look up on the chart? GUA. Why do I look up the GUA? You always use the codon, the message. You always use the message. Okay? So I'm going to look up, what am I looking up? What would we look up here? GUA. So if I look up GUA, I'm going to get valine. So that is the amino acid that I would see there. So tRNA, transfer RNA, if the anticodon said this, GCU, what would be the codon that it would land on?
C.
C what?
G.
G, A. Okay, could you tell me the DNA that this mRNA came from? Yeah, what would you say that it was? Okay, yeah, so you would work if your codon is this, then my DNA would have to be what?
G, C, T.
G, C. Oh, and now why did you say T? Why T's? We're in DNA, and DNA has the nitrogenous base thymine. Okay, you could work your way forward and backwards that way. Is that the same one we did? Yeah, we don't want to do that one again. Okay, then this brought us to mutations. Okay? So mutations, anytime you change the what? DNA. If you change the DNA, you're going to change the mRNA, and if you change the mRNA, you're going to change what tRNAs land, and you'll change what amino acid you have in your protein. Okay? And we talked about things that cause those mutations, errors, mutagens, transposomes, and then we talked about the two categories. One was a frame what? Shift. And the frame is, if your frame can outline 3 bases, right? And if I eliminate, all of a sudden I'm going to shift my frame over, and it's going to be a different 3 bases that I'm going to be highlighting. Okay? And we talked about it in this way. If this is normally my frame, if THE is what I'm looking at, and that's always what I use, and then, oh, I wish those were together. Okay. So if this is my frame, THE, then my next one in the frame is BIG, and then fat, and then cat, and 8. But if I eliminate that E, then my first one is not THE, it's going to be what? THB. Because I've eliminated that B, that E. Sorry, does that make sense? Am I confusing you more? You got it, all right. So then that throws the whole thing off. Then we talked about point mutations. The way I remember this is I'm pointing to one nucleotide and I'm changing it. And sometimes when you change that one nucleotide, it doesn't make any difference. You'll end up with your same product as you would before. We can see that here. It doesn't matter if I'm CCU, CCC, CCA, or CCG. Every single time I'm going to get proline. But here, if I'm UAC, I get tyrosine. But if I'm UAA, what do I get? Stop codon. Is that a big difference? Yeah, all of a sudden you're not going to move forward anymore. And some of these amino acids are polar, some are non-polar, some are hydrophilic, some are hydrophobic. So if you end up changing your amino acid and it doesn't fold correctly in its shape, then that can also be a problem. And that's what we saw right here, okay? So if you have the wrong one in there, and we saw that with sickle cell disease. If you have the wrong amino acid in there, it doesn't fold itself properly. All right, so here is that another one or the same one? It's the same one. And another one of the same one. I have it in there. I think that's it for that. Okay, what's this? Will this be helpful? Okay, we got all that. We're all right. Any other questions or concerns that you have? You know what you have to make sure you do? Additional objectives. What were you going to ask me?
So what would be that E that you're taking out, like in asking?
Oh, if we went back here, let's go to this right here. Okay? So this one that we did, we said, oh, the mRNA then would be what? G, what? U, and then what? A. Right? Okay? If instead this T were gone, then the way it would be G, U, and then what? A again, right? And that's okay because these two are the same. But then my next one starts out U, what? C, C, and my next one would then be what? U, C, whoops, I don't have any more. So I'm throwing them off by doing that. The first one I still ended up getting the same thing, so that would be like a silent mutation.
So it's just doing nitrogenous base.
Yeah, different nitrogenous base. Okay, what else? Questions, concerns? Yes.
So would that be harmful or it's not?
If you end up with the same product as before, then that's going to be a silent mutation. But if you had a different letter here, you know, if this was a CAG right here, if that's originally what the DNA was, then all of a sudden now you're GU, and now all of a sudden you're GU what? C. Now you have a different amino acid that you're going to pick up there. Okay, anything else? Okay, you're super smart. Study. If you're looking at this late on Sunday evening, you waited a long time. Have a piece of toast and good luck. I'll see you tomorrow morning.